On-device small language models need a different context policy. A compact model may advertise a very long context window and still fail much earlier in production. The device may run out of memory, the response may arrive too late, or the model may stop using the information reliably. That is the gap we need to design for. Accepted context is not the same as deployable context. I'm Mehrdad. In this lesson, we'll build a practical context policy for small language models running locally, at the edge, or under tight privacy and cost limits. Here, small language model, or SLM, is a deployment category, not one universal parameter cutoff. We'll use 6 controls: budget, specialize, select, defer, checkpoint, and escalate. Together, they build the smallest working set that remains sufficient and safe for the task. How do we turn that gap into a usable budget? Measure 4 limits separately: the model's accepted capacity, the device's memory ceiling, your response time target, and the longest context the task uses reliably. Do not hide those limits behind one SLM label. Safe active context is the smallest measured ceiling, with space reserved for reasoning and the final answer. This is a production heuristic, not a provider formula. For our offline field service assistant, the packet still needs the current safety policy, the work order, relevant evidence, and enough answer space. Measure that complete packet on the actual device and serving stack. If this lesson is useful, like the video and subscribe for the rest of the context management series. Why does device memory often become the first hard ceiling? Runtime memory includes more than the model weights. It also includes working buffers, serving software, application overhead, and the key value cache, or KV cache. That cache holds temporary attention information for tokens the model has already processed. The weights stay mostly fixed after loading, but the cache grows with the active context. The first pass over the prompt, called prefill, can also create a memory and latency spike. So smaller weights help, but they do not make long context free. Test real prompt lengths on the target system and stop before the first quality, memory, or latency failure. A tablet may accept a long manual and still respond too slowly to be useful. Finally, separate task meaning from machine memory. Your application decides what remains true. The cache policy decides what inference state stays resident. Production needs visibility into both. Once the budget is real, the next question is what deserves to enter it. Once the budget is real, do not spend it on a general assistant prompt. Give the model one narrow task contract, one role, one goal, a short prioritized constraint list, and a fixed output structure. Think of this as a job description that the model can execute and the system can test. In our field service example, the model recommends the next authorized diagnostic action. Its answer includes a likely fault, the exact supporting passages, and an escalation reason when evidence is incomplete. Retrieval, policy checks, tool selection, and final validation remain in the surrounding application. The small model should not have to infer that whole control system from one long paragraph. Specialization reduces competing instructions and makes failures easier to diagnose. Now we can decide which evidence belongs inside that contract. How do we choose that evidence? Selection is not a race to produce the shortest prompt. Recent research on small language models found that compression could preserve evidence that appeared relevant while still leaving the model unable to answer correctly. The same context budget could also help one model and hurt another. So retrieve broadly outside the prompt, then rank, remove duplicates, and preserve enough surrounding text to keep qualifications intact. Safety rules, exceptions, identifiers, and measurements must stay exact. In our packet, keeping the phrase pressure anomaly is not enough if compression drops the unresolved seal inspection. The keyword survives, but the operational meaning changes. Prefer a small, complete evidence set over a pile of fragments. Stop when the selected model passes a sufficiency test, not when a fixed retrieval count is full. The same principle applies to tools and raw artifacts. The model does not need the full diagnostic catalog, every manual, old logs, conversation history, and inactive fields in every request. Keep those resources in an external registry, then admit only the active set through a filter or deterministic allow list. For this step, our assistant may need just 2 actions: read the relevant sensor, and request human review. It does not need every calibration or administration tool. Deferred does not mean unavailable. Stable identifiers keep manuals, logs, and records reopenable, while the model sees only what it can use now. That controls prompt size and reduces tool selection errors. The next control decides where the task state itself should live. A chat transcript should not become the system's database. Organize application state into 4 lifecycle tiers, based on when each item is needed and how expensive it is to reconstruct. Working state enters the current request. Intermediate notes support the next few steps. Durable state records business facts and unresolved commitments. Raw artifacts remain outside until the system needs to reopen them. In our work order, the latest pressure reading may be working state. Open diagnostic questions are intermediate. The unresolved seal inspection is durable state, and the full sensor trace remains a raw artifact. Only the first tier enters every request. Information should live where its future use requires, not where it first appeared in the chat. Different systems use topic clusters, tiered memory, or lightweight graphs to manage this lifecycle. There is no universal winner. Choose the lightest external structure that fixes your measured bottleneck. A flat prompt should not act as working memory, database, and archive at the same time. Even a sufficient input packet can produce an unsafe answer. So validation comes after generation. Check whether the answer is supported by the evidence, whether citations resolve, whether required fields are present, and whether policy and risk limits are satisfied. Accept a supported, low-risk answer. If a specific piece of information is missing, retry with a richer tested profile only when it still fits the latency and cost budget. Otherwise, route the task to a specialist model, a rule-based workflow, or a human reviewer. In our example, missing inspection evidence or a safety-critical restart recommendation goes to human review. Escalation is a control path, not a guarantee. Measure whether validation catches unsupported answers, whether the model declines appropriately, whether routing reaches the right destination, and what the extra control costs. Once those boundaries are clear, we can automate how each request is assembled. Now we can put the policy into one component, a context compiler. This is our system design term, not the name of a published architecture. For each request, the compiler reads controlled sources, resolves the current policy and task state, selects a complete evidence set, and loads only authorized tools. It then applies the model's required chat format, counts the full packet, reserves space for the answer, and rejects or escalates any request that cannot fit safely. Keep every budget configurable until the model, device, serving stack, and risk policy have been tested together. The advantage of a small model is not that it processes everything cheaply. The advantage is that a well-designed system gives it only the information and capabilities it needs. If this context management course has been useful, subscribe to Multi-Agent Academy and connect with me on LinkedIn. I'll continue sharing evidence-backed lessons on agentic systems and machine learning engineering. Thank you for learning with me, and I'll see you in the next one.